In the second lecture for Unit 6, we'll look at queries, distance, direction, and grids within spatial analysis. First of all, spatial queries are important to use in GIS, especially with applications to find distance from a feature, radius of a feature, a centroid within a feature of a radius, how a feature overlaps another feature, attribute queries, where attribute field equals specific values when a feature has a specific set of attributes. And then, of course, using selections for joins and relates, adding additional attribute field information to features to be queried. Calculations may be made using vector or raster data. For vector data, field calculations and geometry calculations are common. For raster data, resampling and combining two or more layers are common factors to think about when looking at raster analysis. The important difference is that vector data is object-oriented while raster data is grid cell-oriented, which means that the functions of calculations for spatial analysis will vary between the two types of data, the two data models. Quantitative data is obviously critical to GIS, and there are several aspects to this that we'll look at. Normalization, that is adjusting quantitative data to provide a simple count, which is used for averages, percentages, and densities. And conversions and calculations are used to create percentage averages and density, for example, the number of cases per square mile. Normalization can be done in ArcGIS under the symbology area. Standardization ensures that data from separate sources are compatible or adjusting the magnitude of a data set to facilitate comparison or combination with another data set. This allows for variation in factors to be addressed in each data set for analysis. Computing the mean and standard deviation for each data set creates a mean of 0 and a standard deviation of 1. This allows data to be compared across different data sets. Density is an important factor in spatial analysis, and it includes point density, distribution, and kernel density. Point density depends on the population variable and the zone-based data. Variations can occur in the density calculation based on the data sets used and the calculation method applied. So, for example, the geographic scale of the analysis is very important. You need to have an understanding of whether you're using, for example, county boundaries in which the dot density might be placed randomly, or census tracts, or other geographic areas. Distribution depends on the type and resolution of the zone data, and kernel density, which is two-dimensional, is produces a smooth tapered surface and weighs values towards the center to reduce values from jumping abruptly and missing values towards the edge of a region. Next, we'll take a look at distance. Cost distance is an important factor that can be studied in GIS. It relates to spatial analysis. This involves the cost or time across a network. Paths and distance may be computed in order to figure out what is the most efficient route. Which variables need to be considered? Distance, slope, obstructions, speed limits, stop signs, stop lights, intersections, mode of transportation, etc. All those things are factors that come into this kind of network analysis. Network distance seeks to find the most efficient route, and routes, especially on routes with multiple stops. Multimodal networks for transporting goods are also considered. Buffering involves point, line, polygon buffers, and buffers may be dissolved in order to create a single feature within the data set. Buffer analysis, raster buffers. The benefits of buffer analysis are numerous. So, for example, if you're looking at point data, you've already seen some of this where you would be using wells within data, and you might want to put a buffer around those to see what the distance is, what objects, what houses, what structures are within a certain distance of that particular area. Then you can dissolve the buffers in order to look at the unit as one single area or region for further analysis. Points, in this case, we have circular buffered with user-supplied radius. Here's buffering a line. Has rounded ends where the radius of the buffer sweeps around. Polygons may be buffered as well. Here's a good example of a point buffer analysis where you're looking at pollution sites, putting buffers around those to be able to indicate areas that are within a certain distance of those polluting points. And here, for example, schools have been added to the data set to see how many schools are located within the buffer of a certain area from those polluting sites. And then population, how many people live within those buffered zones as well. Here's another good example with drug-free zones. So, for example, if criminal penalties are higher for drug crimes that are committed within a certain distance of a school, then the GIS can be used to figure out what the buffer is for those crimes. A line buffer example might relate to businesses within a quarter mile of a selected street being paved. Maybe a city needs to notify those businesses of the construction. And here's the result. And then features may be selected inside the buffer. And there's your selection. A polygon buffer analysis, in this case, parcels within 150 feet of selected property in this case, the city would need to send notifications to adjacent landowners in regard to requested zoning variances. Here's your buffer. And then the individual features can be selected, and you can use that to generate a list of who the affected parties are. Next, we'll take a look at direction. So with linear direction, directional analysis of streams and transportation. With point, distance analysis, how far is the nearest hospital for residents? Distance between bus stops, distance to the bank, retail, or other services can be calculated. Surfaces, directional analysis is related to surfaces. Slope and aspect may be used to determine flow of direction and speed. And finally, grid. Here's the use of grids within GIS. Grid cells typically have a single attribute associated. The z-value is normally the attribute value. X and Y are the coordinates, and raster tools can calculate grids with new meaningful variables. So, for example, you have hillshade, shaded relief, slope, and aspect all being calculated from a single digital elevation model. This is raster data. Then spatial filtering may be used on image analysis for sharpening, blurring, or smoothing, edge detection, embossing. Nonlinear spatial interpolation may be used to examine the data for normality and trends that transform where necessary. This may include hill shading, local averaging to remove outliers in the range. And this concludes this section of the analysis for Unit 6.